Hello. In our first video for section 3.7, we took a look at what is meant by the phrase implicitly defined function. In this video, we'll see that even when we cannot solve for the function explicitly, we can still compute the derivative using a process called implicit differentiation. So usually the function defined, an implicitly defined function, will be too complicated to solve for y as a function of x, but we can still talk about such functions even if we can't work with them directly. Surprisingly, we can still calculate derivatives of such functions, and this process is called implicit differentiation. We're going to finish off this video by looking at two examples of implicit differentiation. The first is this. Let's consider the equation 3y cubed minus 2xy plus 4x squared equals 312. And we're going to say this defines y as a function of x. So we've made the choice here that I'm going to be given the x first, and then I'll put it in that equation and solve for y. Now solving cubics can be very difficult, so we don't really want to bother with trying to find a formula for y, if in fact that was possible at all. Nonetheless, we can still calculate an expression for dy dx, and we can actually calculate the value for dy dx at a point in the graph, the point minus 3, 2. By the way, what this means is that if you put x equals 3 and y equals minus 2 in this equation up here, you will get an answer of 312. So that's what it means to be a point on the graph of this implicitly defined function. So because we want to find dy dx, the derivative with respect of y with respect to x, we want to keep in mind one thing. So we're thinking of y as a function of x. Okay. Now we're going to differentiate both sides of this equation, this given equation, with respect to x. And again, we're going to be thinking of y as a function of x. If you like, to help you remember this, you can replace the y of x, the y's by y of x. This just reminds you that y is a function of x, and then leave the y of x in as you do your work. So here we have then applied d dx to both sides of the equation. The derivative of the constant turns out to be 0, so that's easy. And on the right-hand side here, I just used the fact that the derivative of a sum is the sum of derivatives. So we take the derivative of each of these terms, and the last two cases we factored the constants 2 and 4 out in front of the derivatives. Now we do this differentiation, and all the rules we've learned already, product rule, quotient rule, chain rule, might come into play here. So to differentiate the y cubed, we're going to use the chain rule. Okay, we're going to think of the function y of x as composed with the cubing function to get y of x cubed. And when we address the derivative of x times y of x, that's a product, we'll use the product rule there. So what does this look like? So we've recopied the previous line up here in the top. And so first, let's take a look at this expression. We want to differentiate the y cubed. I brought the factor 3 out in front. If I differentiate the y of x cubed, the cube differentiates 3y of x squared, and by the chain rule I differentiate what's inside the cube, that's the y of x. So here's the chain rule contribution. Secondly, we use the product rule on this piece, PR for product rule. And here we see the derivative of the first function x times the second y of x, and then the first function x times the derivative of the second. And then finally at the end, we've gone ahead and differentiated x to the fourth to get 4x cubed times 4 gives 16x cubed. Do a little algebra. So the 3 times 3 is 9. And now that I've done the derivative, I'm going to drop the of x in the y, and instead of y of x cubed, we'll write y of x squared, we'll write y squared, and the derivative of y is dy dx, and similar changes through the rest of the display here. Now, once you've taken the derivative, we can now solve for dy dx. This is just a simple algebra problem. It's equivalent to solving a first degree equation. We're going to start by bringing all the dy dx terms to one side and then factor out the dy dx. So in the first step here, we've taken the dy dx terms to the left. So here is the 9y squared dy dx. And when we do this multiplication, minus x, that's that term. We've taken the 16x cubed over to the right-hand side, subtracted it from both sides, and find the minus 2xy here, the minus 2 times 1 times y. If I bring that to the right-hand side, becomes the 2y. And then finally, in this last step, we factored out the dy dx from the left-hand side. And so now we can write down the expression for dy dx just by dividing through by 9y squared minus 2x, and here it is. So there's an expression for dy dx that arises from that implicit equation that we started with. Now, once we have such a derivative, we can actually find its value at certain points if we like, and we just do that by plugging in the given x and y values. So the second step is very, very easy. We want to find the value for the derivative at the point 3 minus 2. So we just put in x equals 3 and y equals minus 2 in this expression, and out pops our answer of minus 218 over 15. Now, just one interpretation here. We know that the derivative is the slope of the tangent. And even though, again, we can't find the function we're working with explicitly here, we can make the computer, make Mathematica graph this. So here is a graph of the expression 3y cubed minus 2xy plus 4x to the fourth equals 212. This graph is the set of all points that satisfy this equation. The point 3 minus 2 is over here. You can see it is on the graph, and we've sketched in the tangent line, this line of slope minus 218 over 15. One more example. Let's get into something a little more complicated. The expression tangent t squared times r equals e to the t plus r plus t squared. We're going to say that implicitly defines r as a function of t. So you give me a t value, I put it into this expression, and somehow I come up with the r value that goes with that. So I want to find a formula for dr dt. So we want dr dt, so we're going to differentiate both sides of this expression with respect to t, and think of r as being a function of t when we do this process. So there's the derivative applied to both sides. And once again, we have chain rule coming up. The tangent of t squared r is a chain rule. It's a composition of the function t squared times r with the tangent function. And likewise, e to the tr is a chain rule application. It's the function t plus r combined or composed with the exponential function. So when I differentiate the tangent, derivative of tangent is secant squared. So that comes out down here. And then by the chain rule, I must differentiate what's inside the tangent. So I mark the derivative of t squared r after that secant squared. We'll do that derivative in just a moment. Likewise, for the exponential, the derivative of e to of the exponential is the exponential itself back. And then by the chain rule, what's inside the exponential, we differentiate the exponent t plus r. And then finally, the t squared differentiates to 2t. And in the next line, down at the bottom here, we've used the product rule to differentiate the t squared r. So first function t squared differentiates to 2t times r the second. And then we have t squared times the derivative of r, which is dr dt. And when we do this derivative up here, the derivative of t plus r, the derivative of t with respect to t is 1, and the derivative of r is dr dt. Okay, once again, once we found the derivative, dr dt, or differentiate the expression, we can find dr dt. Again, this is an algebra problem. We start by expanding, so multiplying this expression we have out, and then bringing all the dr dt's to one side. So here's how that happens. Here I've just recopied the expression from the previous slide, and now we just do multiplication. 2tr times secant squared gives that term. Secant squared t squared r times t squared dr dt gives this one, and then likewise similar multiplications to finish this off. Okay. Now we bring all the dr dt's to one side because we want to solve for dr dt. And then we factor the dr dt out of the expression on the left to prepare to solve for it. So this is very similar to what we saw in the previous example. Bring the dr dt's to one side, everything else to the other, factor out the dr dt, and then finally we can solve for dr dt and get this expression for the derivative. And then finally, this was a pretty complicated function. What does it look like? Well, I have no idea, but Mathematica can be forced to graph this relation. So here is the graph, believe it or not, of tangent t squared r equals e to the tr plus t squared. This is a graph of all the points rt that satisfy this equation. So it certainly is not the graph of a function, and we can see there are lots and lots of functions implicitly defined with this relationship. And that's the end. Bye.